Time to talk about how oxygen is transported in the blood. It mainly does this via red blood cells, but we also get some transport of oxygen in the plasma. So when we think of red blood cells, erythrocytes, I think of hemoglobin. Hemoglobin can carry oxygen, and it carries 4 oxygens in its hemoglobin, in its saturated state, I should say. And when we put the little light laser on our finger and it says we're 98% saturated, that's telling us that our hemoglobin is essentially full. So full. The other 2% is in solution. O2 is in our plasma floating around. So we essentially get 20 milliliters of O2 per 100 milliliters of blood. That's how it works out. And based on our percentages, we have approximately 0.5 milliliters of O2 dissolved in plasma. And then we have 19.5 milliliters O2 attached to hemoglobin. And this gives us our 20 milliliters of oxygen there. So this is what we're really interested in, is the hemoglobin aspect of this. Because this allows oxygen to be reversibly bound to the hemoglobin and enables it to be offloaded or loaded very easily. It's a cooperative reaction. So a cooperative reaction in biochemistry means that once a molecule binds to another molecule, if they're cooperative, it's going to make it easier for the next molecule to bind, and then so on. The affinity, or the amount that the molecule likes the other molecule, increases. So they kind of like each other at first, and then once the next molecule binds, they like each other a little bit more. By the third, a little bit more. And by the time, let's look at it from like human aspect, by the time 4 oxygen binds to the hemoglobin, it's like they're getting married. They like each other so much. But this is a reversible reaction. So let's remember that at the red blood cell levels, it's full of hemoglobin. And then oxygen is reversibly bound. It just means it can go on and off. And it looks like this. Hemoglobin plus O2 loaded in the lungs yields HB bound to O2. And then reversibly, as you might think, this is unloaded to tissues. So oxygen needs to come off this way. Look a little simpler if I did it that way, but you get the point. So our blood also has different colors over here. So when we're over on this side and there's no oxygen bound to it, it's a very deep red. Versus over here with oxygen bound, it's a bright red. And we call this oxyhemoglobin versus deoxyhemoglobin. So when we load it, all of these things, we need to take account all of our gases that happen in the lungs. So when we're loading it, we have a decreased carbon dioxide, temperature's decreased, hydrogen ions are decreased, and we have an increased affinity at that point for O2. So the lungs give us this really cool thing that allows for the affinity of O2 to be increased. And this unloading is due to the Bohr effect, which we'll talk a little bit more when we talk about the bicarbonate system. And now that we've talked a bit about hemoglobin, we want to know that hemoglobin's measured clinically. It's one of those things that when you go get your blood test, they're They're going to measure your hemoglobin count or concentration. It's usually around 12. I don't remember the unit off the hand, but they also are going to measure your partial pressure of O2 in plasma. Remember, if we can get the percent of hemoglobin and the percent in plasma, we can figure out how much of the 20 milliliters of oxygen are actually getting to tissues. So when we unload oxygen to the tissue, what ends up happening is I'm going to write it this way. We're unloading it. We're going to have an increase in CO2 concentration, an increase in hydrogen ion, and an increase in temperature. These are the exact opposite of what we see in the lungs, where, let's just say loading O2. We're going to have decreased CO2 concentration, decreased temperature compared to the working tissue, because remember, making ATP requires waste heat, and then hydrogen ion or acid concentration is low, and this is going to yield an increased affinity for HB hemoglobin O2. So at the tissue though, since we wanted to load it, we wanted to get oxygen from the air onto the hemoglobin so that it could travel through the bloodstream, get to the tissue. We needed different conditions to motivate, if you will, the oxygen to come off the hemoglobin. Because remember, by the time that fourth oxygen binds, they really, really like each other. So we have these conditions here, which decrease the affinity. Or once again, affinity just means how much hemoglobin and oxygen like each other. And this is going to allow O2 to be unloaded. So we've got three different conditions right now. Our carbon dioxide, our protons, and our temperature, our pH. We also have another molecule called DPG, diphosphate glycerate. And what this does is when you're exercising, this DPG maintains the binding site that oxygen normally, let me start over. DPG will occupy the binding site for oxygen in the T state, or the low affinity for oxygen state. This way, there's something bound up to the four binding sites on hemoglobin. So let's talk about, we'll put right here, temperature, pH or hydrogen ion content, and then DPG. We'll have two conditions here. Increase in affinity, decrease in affinity. Okay, so now that we set the stage for everything, we have this nice little graph I've started, and it's going to start looking like this. So we have on the bottom 20, 40, 60, 80, 100, 120, 140, O2, this is the partial pressure, O2 in millimeters mercury. Over here we have our O2 content in milliliters per 100 milliliter of blood. On this side, our hemoglobin saturation. Remember, it's in percent. Okay, so now that we've set the stage there, life exists for us in this area. So in normal conditions, we will be, under normal cellular respiration, we'll be offloading right around here. And then, so right here is our, remember our PO2, our venous O2 is 40 millimeters mercury. And remember our systemic artery, our PaO2 was 100 millimeters of mercury. So we're offloading here and then at there. and we can have the sigmoidal curve that looks like that. So from there, this gives us our hemoglobin, but we have the last 2% is the plasma. So this is under normal conditions. As one oxygen binds, another oxygen binds, another oxygen binds, and we get to the fourth, we can see that this is our cooperative mechanism here. So if we have a decrease in temperature, so this is 37 degrees Celsius, this is our normal operating temperature. If we were to decrease our temperature to 20 degrees, we're going to increase the affinity for oxygen. We're going to hold on to it a little tighter. And it's going to look like this. So we're going to shift this way. 20 degrees C. So if we, and as we increase our temperature, let's just say we're exercising really hard, we're going to make it a little easier for us to offload our oxygen. So we'll decrease our affinity, so it will come off a little bit easier. Okay, so when we're exercising, though, we also produce hydrogen ions via glycolysis, the byproducts of that. So we also get a little bit different oxygen offloading from that. So this is due to our pH. So an increase in pH is going to signal that we're exercising, producing hydrogen ions, and that it might be beneficial to make it a little easier for us to offload oxygen. So we're going to decrease the affinity for oxygen, make it easier for it to come off. And if we were doing the opposite, we were sitting around not producing many hydrogen ions, we're going to shift it to the other way, increase the affinity.